Hey, yo, big man, you got a ruler by any chance? I think mine's broken. What do you mean broken? It looks fine. Keep trying to measure this tin, but the length keeps changing by like 2 millimeters every time, saying 23.0, 23.2. Need the exact measurement, you feel me? Brother, that's not because of the ruler, man. It's because of random error. Random error is mainly a result of human error. In this case, you're not able to line up the ruler accurately every single time, so your measurements are going to vary by a few millimeters. And what about this lotion though? It says 50 grams, but every time I weigh it, it says 45. Is that human error as well, or am I being scammed? Brother, you're not being scammed, G. You probably haven't zeroed your scale properly. That's why your readings are off by the same amount each time. This is called a systematic error. Oh, okay. I see, man. I get you. You're a smart guy, you know. Don't worry, man. What are you doing with all that lotion and the Pringles tin anyways? Now, every measurement that you take has some sort of uncertainty. And this uncertainty can be represented by this plus or minus sign. So you have a value, let's say 5, and it can be represented by that plus or minus 1. This is your uncertainty of every measurement that you take. Now, there's two main types of errors that lead to uncertainties. The first one is, as we came across, was random error. Now, this is mainly due to human errors. We're not machines. We're not precise every single time. And an example of this could be, let's say you're seeing how fast something can move along a track and you're timing it with a stopwatch. The reaction time would be the human error or the random error in that case. Also, if you had, let's say, a reading up here and you were trying to measure the level at which it's at, that's called the parallax error, because if you notice, if you look at the level up and down like this, you'll see that the reading changes. And when you're reading this kind of thing, you want to make sure that your eyes are perpendicular to the level of whatever it's reading. So that's again that's a parallax error, and it's a type of human error, random error as well. The good thing about random error is that you can reduce it simply by taking repeats, taking multiple repeats of the experiment and getting different values and finding a mean. The other kind of error is a systematic error. And this is an error in the way that the apparatus or system is set up. So the easy one is a zero error, which is where, let's say I have a 50-gram block and I put it on a scale and the scale says 45 grams. If you then remove the block and it says minus 5 grams on the scale, that's a zero error, because you haven't clicked the zero button on the scale to make sure that when there's nothing on the scale, it reads the correct value. So that's called a zero error, and that's a type of systematic error, probably the most common type. What you notice about systematic errors is if you have a systematic error in a data set, you'll notice that every single value is off by the same amount. Now, before we move on, I want to talk about the two types of uncertainties. So first of all, you have an absolute uncertainty. And this is a uncertainty given in the units of the measurement. So let's say you're measuring a piece of, I don't know, whatever it is, the length of something, and it's 5 centimeters, plus or minus 1 centimeter. This plus or minus 1 centimeter is your absolute uncertainty. The other kind is a percentage uncertainty. And that can be calculated by doing the absolute uncertainty over the actual value times 100. So in this case, it would be 1 over 5 times 100, so that's 20%. But we need both of these errors because these uncertainties, because they can both be useful in calculations. So where can you find uncertainties for different equipment and measurements, whatever? Sometimes they are given in the question, or if you're in a practical sense, they can be given by the equipment. Sometimes if you look at a mass balance, or say on the bottom 50 grams plus or minus 0.01 grams, for example. Yeah. So sometimes it's given by the equipment, the apparatus. If it's not given by the apparatus, there are some kinds of measuring devices that have specific uncertainties. And in this case, what you do is that you see that the uncertainty is equal to the smallest graduation and divide that by 2. So half the smallest graduation. An example of this could be like a thermometer. So if you have a thermometer and it has loads of like markings and you have your line for the thermometer reading temperature, you notice that the smallest difference between each value is 1 degree Celsius. Yeah? Each increment is 1 degree Celsius. Therefore, the uncertainty in this case would be 1 over 2, so plus or minus a half degrees Celsius. That's your absolute uncertainty for this scenario. Now, before we move on to the next one, there's a very key point I have to go through. It's a difference between readings and measurements. Readings are one-judgmental. An example of this is, as I said, the thermometer, where you're just taking the reading and you're getting a value back. Another one could be like a mass scale. So you put a block on a weighing scale and it says 30 grams. Yeah? You're putting something and the apparatus or the whatever measuring device is simply giving you back a value. That's it. It's just giving you back a value. A measurement, on the other hand, is too judgmental. This could be, for example, a ruler. And let's say I wanted to measure an object here. So I've got my markings. And I have an object. Right? Now you might think, in order to measure this ruler, you just have to see where this point goes and take that value. That's not entirely correct. Because you need to make sure that this value here is lined up with 0. You need to make sure that the first point is lined up with the 0 marking as well. And that also leads to an error, which is exactly the same as the smallest graduation over 2. And the main difference between these two is that you can notice that here, in measurements, when it's too judgmental, for example a ruler, the uncertainty is actually doubled because you're technically taking 2 readings, one for the 0 and one for the length value. So you all know that a ruler has a 1 millimeter smallest graduation. So the absolute uncertainty is equal to 1 millimeter over 2, but because you're taking 2 readings, you times that by 2. That's plus or minus 1 millimeter. Now let's say you have a value given in the question or a value whatever, and you're not told the uncertainty of the equipment, and it's not a known measuring device like a ruler or a vernier caliper or a micrometer. These are stuff that you need to remember the uncertainties for. You can find them online. But let's say you're not given it and you're just given a value of, let's say, you're told that the mass is equal to 45.039 grams. And you're told what is the uncertainty of this. And it's not given in the question. And you know that a weighing scale is not something that has a specific uncertainty or any smallest graduation. So in this case, what you do is you simply look at the lowest significant figure. In this case, the lowest significant figure is in the 1,000th unit. So the 1,000th unit is therefore plus or minus 0.001, and that is your absolute uncertainty. So we've looked at how to find errors and uncertainties for given values, but let's say you're given a range of values, a set of data. So let's make up some data. Let's say you have a variable d, and you're told you have 32.8, 33.1, 33.0, and 28.7, and 33.3. Actually, you know what? Let's say 32.7. Okay? So you're given some data. Now, the first thing that you have to do when looking at this data, before you make any sort of calculations, is to look out for any anomalies. You can clearly see that this value here, 28.7, is very different from all the other values. All these other values are around 33-ish. This is around 5 less than that. That's a clear anomaly. So we discard that from all our calculations. So let's say I want to calculate the mean. Probably know how to calculate the mean. You sum all the terms and divide it by how many terms there are. So in this case, I'm going to add everything plus 33.0, ignoring the anomaly. And I have 4 terms there, 1, 2, 3, 4. So I divide by 4, and then I find the mean. And in this case, the mean is 39.1. So how would you find the uncertainty in this case? Well, the absolute uncertainty, we have come across it before, is simply half of the range. And the range is the largest value minus the smallest value. Again, you are going to ignore any anomalies. So in this case, that would be a half times 33.1 minus 32.7. That is equal to 0.2. Now, the reason why I calculated the mean was because if I wanted to say, let's work out the percentage uncertainty, usually you would take the absolute uncertainty divided by the actual value times by 100. For this case, you're given a range of values. So instead of using the actual value, we use the mean in this case. So to find the percentage uncertainty, I would use 0.2 over 39.1 times 100. And that will give me my percentage uncertainty. Now the last case of uncertainties is uncertainties within graphs. So if I wanted to draw, when I have, let's say we have a graph here, the first thing that you always want to try and do, sometimes usually the question will ask you to do it, sometimes I'll give it for you, is to draw the best fit line. It's usually the first thing that you always want to do. So you want to try and get the line as close to all the data points as possible. Obviously a straight line, I don't really have the feature to do that, but use your ruler. The one thing you need to make sure is that the straight line goes through all the error bars. Let's say you want to work out this line of best fit. The best way to do that is to use the data points that it goes through. Now, you want to make sure that these data points are as far apart as possible, but you also want to make sure that they are on the line or very close to the line. So if I were to pick the furthest 2 data points, I'd pick this one and this one. But you can see that this data point is quite far from the line. So in this case, I'm actually going to choose the first one and the second to last one. And let's give these some values. Let's say this is a value of 10, as a value of 4. Let's just say this is 10. Let's say this is 20, and let's say this value here is 80. Okay? And we're going to go ahead and calculate the gradient. So m here sounds like the gradient, so I'm saying m best for the best fit line is change in y over change in x. And if you want to draw a triangle, feel free to draw the triangle and do that. Or you can just say change in y is 80 minus 20 over 10 minus 4. And that will give you gradient of 10. Now one thing that you have to be careful about is, in this case I haven't included any, but if there are units, make sure that you put the units in. So let's say this was in grams, this is in centimeters, this unit would be grams per centimeter. Now in order to work out the uncertainty of a gradient, you have to actually draw something that's called the worst fit line. And this is the maximum possible steepest line or the shallowest possible line that goes through all the error bars. And the best way to do this is to try and select the bottom error bar of the first one and the top one of the last one. And you draw a point. Notice here how it misses a few error bars. So in this case, I wouldn't actually choose the top one of the last one. Again, I would actually go down and probably go for the second last one. Connect them up. It goes through all the points, all the error bars. And again, use the error bar values. Use the error bar point values. So in this case, let's say the value here was 18 and up here was 84. Then my m worst is equal to change in y over change in x. equals 84 minus 18 over 10 minus 4. So that is 11. Now the other way you can do it is by picking the, the shallowest gradient, which would be, in this case, the top one or this one. And you try always to go for the first one. So you try the last one, and yes, it would go through. So that would be your shallowest. Obviously, I'll aim it better, draw it better if you were on the exam. But you can also do it that way. And they should give you similar or very, very close uncertainties. Both either choosing the steepest line or the shallowest line, both are acceptable. Now to calculate the uncertainty in the gradient, call it change in m, is simply m worst minus m best. And that is just 1. Remember your units, by the way. If you wanted to find out the percentage uncertainty, you would do the absolute uncertainty in the gradient, which is, it'll be better if I say m worst minus m best over m best, your best fit gradient, times by 100. So in this case, it'll be 1 over 10 times 100. That's plus or minus 10%. Now, a quick tip for any sort of questions in your exam when you have to describe a practical or think about a practical for a certain scenario, or in your practicals that you're doing in school, is let's say you had a pendulum and you were recording the time it takes to go and make one oscillation, to go back and forth once, measuring this whole time, and we'll call that t. Now, the simplest way you think about doing that is, okay, get your stopwatch and measure from the pendulum to go from this position to this position and back there again. You'll measure one oscillation. So let's say you take an oscillation and it comes out as 3 seconds. And let's say that the error or the uncertainty in this measurement is plus or minus 1 second. Now, this is actually quite an inefficient way to do this. You actually want to find a way that you can reduce the uncertainty. And remember what I said about random error, and that taking repeats reduces the random error in a result. So the better way to actually do this is to maybe calculate the time it takes for 10 oscillations. And you start your stopwatch, measure the time. Let's say it comes out as 29 seconds. The error in measuring these 29 seconds is still plus or minus 1 second. So when you divide this by 10 to get time for one oscillation, you see that your error is that your actual value is actually 2.9 seconds plus or minus 0.1 second. You can see that the error in this case has decreased by a factor of 10. So in any sort of situation where you're measuring time of an oscillation or anything similar, try and get between 5 to 10, maybe even up to 20 oscillations, and then divide it by that number to get a more accurate answer with a lower uncertainty. Now, the last thing I want to go through is combining uncertainties. Let's say I had two values and I wanted to add them or subtract them. Let's say I'm given 5 centimeters plus or minus 0.1 centimeters, and let's call that value A, and B is equal to 6 centimeters plus or minus 0.2. Now, if I wanted to add these two values, if I want to say, well, what is A plus B, including the errors, well, you know that 5 plus 6 is 11, so your actual value is 11 centimeters. And the total error in this case is found by simply adding the absolute uncertainties. So in this case, it will be 0.3 centimeters. Now let's say I wanted to subtract them. So I wanted to find out what is B minus A. Well, B minus A is 1, well, 6 minus 5 is just 1 centimeter. But you still add the absolute uncertainties. So the total error when finding out A plus B, B minus or B minus A, is still 0.3 centimeters. So when adding or subtracting, you add the absolute
uncertainties. Now let's look at multiplying or dividing. And let's use the same case of A is equal to 5 centimeters plus or minus 0.1 and B is equal to 6 centimeters plus or minus 0.2. If you wanted to find out AB, well, you know AB is just 30 centimeters squared. But what would you do with the errors? In this case, what you want to do is find the percentage uncertainty in A, which is done by 0.1 over 5 times 100, which is just 2%. And you also want to find out the percentage uncertainty in B, which is 0.2 over 6 times 100, which is equal to plus or minus 3.33%. And here what you want to do is you want to add the percentage uncertainties. So you'll get plus or minus 5.33%. And again, if you wanted to find the total absolute uncertainty, you do 5.33 over 100 times by 30. And that will give you your absolute uncertainty. And the same goes for dividing. If you wanted to find out B over A, which is just 1.2, you still have plus or minus 5.33% percentage uncertainty. When multiplying or dividing, you want to add the percentage uncertainties. Now the final case is where you're looking at powers and roots. Let's say I had a value D which has 30 plus or minus 1.2 meters. This is one way to write your value and its error. You can put brackets around and the unit outside. And let's say I had a value capital E which is equal to D squared. Now we know that 30 squared is 900. But again, what do you do with the errors? Once again, you have to find the percentage uncertainty in D, which is 1.2 over 30 times 100, which gives you plus or minus 4%. And in this case, you want to multiply the percentage uncertainty by the power. So here the power is 2. So you do 4 times 2 equals 8%. So your value for E is 900 meters squared plus or minus 8%. And 8% of 900 is 72, so you could also write it like this. Now, if I was trying to work out let's say you have another value f, which is equal to the square root of d, it's actually not different at all, because you know that you can rewrite square root of d as d to the power of a half, which means you can still multiply the percentage uncertainty, in this case plus or minus 4, by the power. So the new percentage uncertainty in this case is plus or minus 2%, and you can go by your calculation in the same way. So what you always want to do with powers and roots is multiply the percentage uncertainty by the power. Now that's it for errors and uncertainties. Hopefully this has helped you, and I look forward to seeing you again. Please like, subscribe and comment if you want to see more videos like this.